will still trickle in. Maybe we should give them a minute or two.
The trickle-in theory. Okay, great. So remember last time we were giving an example of the sort of anatomy of a process at next leading order. And we considered one of the very simplest cases of production of the Z boson and anything else at the LHC at a PP collider. And we discussed how we factorized the process into a short distance cross-section multiplied by some parton distribution functions or probabilities for finding quarks and gluons sort of one at a time inside the proton as a fraction of the proton's longitudinal momentum along the beam. And then we identified two types of contributions to the next to leading order cross-section. One came from interfering the Born amplitude, shown here, sort of reversed, where you have quark, anti-quark annihilating into a Z. So that's the Born level contribution, and then we interfere it with the one loop contribution, a representative diagram of which is shown here. Actually, it's the only diagram in dimensional regularization. It turns out that the other guys vanish. So we interfere these two with each other. So that's the form of the virtual corrections. And then we also have real emission corrections, where, for example, the quark, before it annihilates with the anti-quark, it radiates a gluon. And that happens with 1 power of the strong coupling, but then we're going to square this, so that gives us our second power, and it's the same order as the virtual correction, where you see both of the powers of the coupling GS here and here. So that is one of the real corrections. And then there's a second type of real correction, where instead of having an initial antiquark, you replace it with a gluon. And then the gluon, before it annihilates, the gluon doesn't directly couple to the Z, but it can couple to a quark line, which runs through the process like this. And in some limit, it looks like a gluon splitting to a quark and an antiquark, and then the antiquark coming in and annihilating to form the Z. And of course, this should be squared too for a contribution to the cross-section. And then we also discussed yesterday that all of these contributions, these three contributions, and there's another contribution where I have anti-quark gluon that looks very similar, so I didn't, maybe I should just list it here. Very similar. So each of these contributions has divergences. This one has a collinear divergence, because if the gluon splits and the quark and the antiquark are very parallel to each other, I mean, I'm going to show you some of this in more detail after we calculate some amplitudes, but there's a general factorization formula that we have at the amplitude level that looks basically like this. If we have a endpoint tree amplitude for a bunch of partons, and we take two legs, A and B, in there to be parallel, and we take, that means that they're proportional to the same vector. So we'll define Kp to be Ka plus Kb. And we'll take Ka to carry the fraction z, and Kb the fraction 1 minus z. So we have a generic amplitude, except that two of its legs are almost parallel. This factorizes into an n minus 1 point amplitude, where we replace legs A and B with the sum of their momenta, p. And that will be almost on shell, because Kp squared is Ka plus Kb squared, and Ka squared and Kb squared are 0. These are massless particles. So this is 2 Ka dot Kb. So if Ka and Kb are parallel, then this thing's proportional to either Ka squared or Kb squared, and it's going to 0. So this thing will factorize, and it will have a factor in the denominator, which is has the square root of Kp squared in it. And there are certain phase factors. But it has a universal behavior where you get some splitting amplitude that depends on A and B. It also depends on the helicities of A and B and the helicity of the intermediate state, P. So we represent this factorization by these blobs, where this is an minus 1, and this is the splitting fraction. So I'm just telling you this now, and later on we'll sort of see it in action, and we'll even calculate some of these splitting amplitudes. But using this formalism, the fact that there's this universal factorization, we can apply it to the case of a 4-point amplitude. For example, the 4-point amplitude with but I have to sort of draw it the right way. Well, anyway, I'm going to draw it in a slightly twisted way. So one application of it is to this upper process, where it tells us that there's a universal way that this amplitude factorizes. And when you square this relation, you get a similar factorization of the cross-section of this square. And so that there's a universal collinear divergence, which goes as the 1 over the invariant mass. So this is Kq plus Kg squared, or 2Kq dot Kg. And it's also proportional to the transverse momentum squared of the outgoing gluon. In other words, this quark is coming in exactly along the beamline. If the gluon continues to go exactly along the beamline too, then those two vectors are proportional and you get 0. But if the gluon comes a little bit off with some transverse momentum, you get a behavior that goes like 1 over Kt squared. And when you integrate over the transverse momentum of that gluon, you get a measure that goes like dkt squared. So you get a log divergence. So that has to do with the collinear singularity that's generated both from this process and also this process. And then last time I mentioned in passing, and again this is something we'll be able to demonstrate later when we have some amplitudes under our belt. But if we this splitting is characterized not only by the angle that the gluon comes out with, but also what is its energy as a fraction of the quark's energy. And we often call that one 1 minus z, and the thing that goes into the collision z. And this probability of a quark to remain a quark as it goes into the collision, it has a 1 over 1 minus z as z goes to 1. And this is a soft singularity. So there's a region of integration where z goes to 1, where this thing diverges, and that will generate, so this generic one here is the collinear. And then there's a second soft in this case. But when I was answering Anthony's question about the gluon distributions, I mentioned that when the gluon splits to QQ bar, this one doesn't have a soft singularity. It's smooth as z goes to 1. It just has a collinear one. So then the final thing I want to show you is the soft and collinear virtual divergences. Well, mostly just soft for simplicity. But any questions about the sort of generic collinear structure? This is completely typical for any next to leading order QCD calculation, but it's easiest to see it in this very simple toy process. But I realize it might not be that familiar to you, so any questions at this time are welcome. Okay. So I wanted to then talk about the virtual divergence, focusing on the soft or the soft plus collinear overlap. But if we have a very soft gluon, then that should be something that's very long wavelength. And so for some generic process, if we exchange some soft gluon, it shouldn't really be able to see into the heart of the process. In other words, if you look at some diagram inside this process, then there will be, and then you want to identify a loop momentum here. And send it to 0. Then generically all the other loop momenta, well, they'll be related to this loop momentum by the external momenta. But if the external momenta are all generic, then these momenta will all be characteristic of the scale of the external momenta. And so as this goes to 0, these momenta will all be happening at a much larger scale, or in distance, they will all shrink to the origin. So these will all be large virtuality. And so we can sort of shrink the picture down to a point like that. And also, if this momentum is very small, and if we call this momentum, I don't know, k, then this momentum L plus k is approximately equal to k. And similarly, our k1, k2, this will be L minus k2. They'll be approximately, this is approximately equal to L. approximately equal to, now what am I doing? L is going to K1 and K2. So these legs here will be approximately, these momenta will be approximately equal to these momenta. So this graph looks just like a tree amplitude. And so we can expect another kind of factorization, kind of analogous to this collinear factorization, where we will find a universal formula for what you have to multiply a tree amplitude by to get the soft behavior of the loop amplitude. And we can basically just calculate it by coupling, by exchanging a gluon between two generic hard lines. In fact, this long wavelength gluon is very classical. So it doesn't even see the spin of the hard particles that it couples to. So for the gluon or a quark hard partons, they're basically equivalent up to color factors. So it only sees the color of the soft gluons can tell what color it's coupling to, but not the spin. To demonstrate that, we can just calculate a couple Feynman diagrams. So we can look at the three gluon vertex. So generically, the three gluon vertex looks something like, might have some labels A, B, C, mu1, mu2, mu3. And it involves the Lie algebra structure constants for the gauge group. And then it has a term with the Minkowski metric coupling together these two indices. And if this is K1, K2, and K3, it has another term that takes K1 minus K2 and gives it mu3. And then it has a few more terms which are related by cyclic symmetry. So that's the three gluon vertex. If we now specialize this vertex to the soft limit, so we take A and B to be the hard colors and S to be the soft color, and I'll give this a momentum minus P and this a momentum P minus K, and I'll take P to be much greater than K, the soft momentum. Then you get this mu1, mu2 term multiplies the difference of these two momenta when they're treated as outgoing. And I made this minus P outgoing and this K. And this still has mu1, mu2. I'll give this another Lorentz index nu, since it's, well, soft. So then this has a minus 2p plus k nu, and we can neglect this term. It also has a term that couples mu2 to nu with a p minus 2k, and it has a eta nu mu1, k, which we drop, p mu2. Now, if we imagine that this guy here is an external line, then it will have a polarization vector that this mu gets contracted with. And it will be the polarization vector for momentum p minus k, but that's basically p, so let's just call it p. And that has to be, as you learned in your QED class, has to satisfy epsilon 2 dot p equals 0. So when we see a p here, it's going to get contracted with epsilon 2, and that's going to give 0. So this line doesn't matter. Also, this p is contracted with indices in here, and now I'm going to make a clever choice of gauge where that propagator is treated transversely, and then I can drop these terms. And then the only term that's left is a term that just shuffles the polarization of this line that's coming out and identifies it with the polarization of the external line, and then a factor of minus 2p nu. And so the main thing I want you to notice is that you just get some factor proportional to p nu coming out of here, and then something that's the identity matrix in the sort of space of polarizations or spins of the gluons. So now we're going to do exactly the same thing for emission off a quark line in order to show you that the answer has the same generic form. And in this case, I should probably take a generator in the fundamental representation, because that's what quarks are in. And then I multiply it by this vertex here is like the vertex in QED, apart from the color factor. It has a Dirac index, gamma mu, on it. And this propagator is a 1 over p slash minus m, standard Dirac propagator. We're setting the p slash to 0. And I'm going to make it p slash over p squared to make it look more like the propagator of a boson. This has a 1 over p squared type propagator. So that p slash is here, and then there's a gamma mu. And then we have a spinner for the outgoing particle with p minus k. But again, k is very small, so this is just like the spinner for u of p. And now what I'm going to do is I'm going to anti-commute this p slash. Remember, p slash is p mu gamma nu, p nu gamma nu. And gamma mu, or gamma mu, is eta mu nu. So when I anti-commute this past, I get a factor of 2. This is 2 p mu. And then that multiplies u, but this is doesn't have any Dirac structure to it. But then I get another term with minus gamma mu p slash u of p. And then I use the massless Dirac equation to conclude that this vanishes. So in both cases, I get a factor which is the generator of the Lie algebra in the appropriate representation for the particle, which in the adjoint representation is equivalent to the structure constants times something proportional to p mu. So this is called the sort of soft emission, or IConnell factor. So by doing it for two different types of particles, one with spin 1 and one with spin 1/2, we see that it just doesn't care about the spin, as I suggested to you from the classical nature of this long wavelength emission. And it only cares about the color in the appropriate representation. Any questions? Yeah, so which type of particle, the gluon or the quark, has larger color charge? So what do I mean by color charge? I mean, I wrote down a matrix here, but a matrix isn't a number. It doesn't have a single size. So what I really mean by color charge is that when I do this particle in representation R and I radiate a gluon, maybe I could compare it by sort of squaring this color factor. That is by taking the gluon, multiplying it by the factor for emitting a gluon of color A, multiplying it by another factor which might correspond to absorbing the gluon, maybe on another line. And then I can sum over A equals 1 to the dimension of the group. That's the dimension of the adjoint representation. Does anybody know what this object is called? Quadratic Casimir operator, right? So there's some C of R times the unit matrix in the color representation R. Good. So then you just need to know, or need to calculate, these color factors. And the case of gluons, we need what's called CA, and it's basically computed by putting together FABC with FBCD, which is CA delta AD. Anyway, with the standard normalizations in SUNC, this factor is NC, whereas for quarks, this is called by QCD people CF, but it's the Casimir in the fundamental representation. And it turns out to be NC squared minus 1 over 2NC. And now for QCD, we get to plug in NC equals 3. And this becomes 3 squared minus 1, or 8, over 2 times 3, which is 4/3. So CA over CF is 9/4, or 2.25. So if everything else is equal, gluons like to radiate soft gluons at a rate which is about a little over twice as much as quarks. This is coming back to Miriam's, when I was talking about the Higgs cross-section and how unstable it was. One of the reasons is that when two gluons come in and form a Higgs, it looks, as far as this soft stuff is concerned, very similar to having a Z when you radiate in the real or in the virtual. You get, the difference is that you get a relative color factor of CA over CF, which is bigger for the gluons. So this is one of the reasons why the Higgs cross-section has a much worse perturbative behavior than the Z cross-section, and it's much harder to get good accuracy on it. There's a second reason too, which has to do with how fast the relevant parton distributions are falling. The gluon distributions are dropping much faster than the quarks are, and that also makes a bit a difference too. Okay, so we have this formula for soft radiation where we didn't really specify whether this was real or virtual. It applies in both cases. And if you think about the kinematics right, from this you can derive the real emission behavior that goes like 1 over 1 minus z. That this has in the square, it has a factor of c, of the representation, whatever. In this case, it would be CF for quarks. But now I want to take that soft emission vertex and make a simple loop diagram out of it. So Z is characterizes the collinear splitting. So we have, so I kind of switched variables on you. In other words, there's a variable that describes soft emission, which is sort of how big the momentum is. There are these small momenta there. But if the soft emission is also collinear, there's sort of a consistency between those two pictures. And in the collinear case, if Z is a generic number between 0 and 1, not at the endpoint, then that's not soft emission. That's strictly collinear, because both particles are hard. They both have high momentum. But when you go into the limit where, say, Z goes to 1, then this particle is soft and collinear at the same time. And so you can see this sort of emission pattern in the overlap between the soft and collinear. Thanks for making me clarify that. Any other questions? Yep.
So collinear refers to the gluon being collinear with the incoming quark from the bottom splitting.
Yeah. And so let me also use that to clarify one more thing. There's two ways you can go collinear. One is called time-like collinear, and one is called space-like collinear. I drew this picture as if it was time-like collinear. Why do I call it time-like collinear? Because if these two particles are in the final state and you calculate the invariant mass between them, you'll find that Kp squared is 2 times the energy of A times the energy of B times 1 minus cosine theta AB. And that's always greater than 0. If you have two particles, their invariant mass that are both in the same direction, both outgoing, their invariant mass is always positive. So this is what we call time-like. When the virtual guy, the one that isn't quite on shell, has Kp squared greater than 0. But the same picture is generic enough to handle the space-like case too. This is a space-like case. This is a dot product between a momentum that's in the initial state and a momentum that's in the final state. And if you work out this dot product, you get a relative minus sign. So this, in this case, this is the thing that we're calling Kp squared, and it's less than 0. And that's what we call space-like. So you need to have two pictures in your mind at the same time. In the time-like case, you have many particles coming out of the process, and then two of them are going parallel, and they're right next to each other physically. In the space-like case, you have an initial particle that was there, and then it gets destroyed, and then there's a collision, and then there's a final state particle. But that final state particle happens to be very close in direction to where the initial state particle was going before it entered the collision. Yeah, because there's a Feynman graph that has a propagator that has a 1 over p squared in it, or 1 over Kp squared. So it's natural to get a divergence. Well, in this case, it's a quark. And in this case, the quark has an extra p slash in the numerator. right? P slash over P squared. So in fact, it's 1 over the square root of Kp squared at the matrix element level, at the level of the Feynman diagram. So this propagator here has a Kp slash over Kp squared, and I'm doing a little hand waving, but generically this is kind of like 1 power of Kp. So it's going like 1 over square root of Kp squared, and that's what I advertised here. Let me give you another sort of explanation, which is suppose we had just phi cubed theory. Then we would have a field phi, which has helicity 0, splitting to 2 other fields phi. And this, the Feynman rule for phi cubed theory is you just put a 1 there. Then we would literally have, at the amplitude level, 1 over Kp squared. And that would lead to much worse divergences than we actually have. At the amplitude level, we actually have square root of Kp squared. So more of the question is, why isn't the collinear divergence worse? Because we have this propagator here that looks like it's going to give us, when we square it, a 1 over Kp squared squared. And the reason for that is angular momentum conservation. If you look at every process that you have in QCD, there's always a violation of helicity conservation by 1 unit. So let me give you an example. So here's a bunch of QCD vertices, and I'm looking at them in a collinear limit. So I have plus or minus 1. Gluons don't have any longitudinal polarization. They're transverse like photons, or left or right hand circularly polarized. But if you want to factorize them onto some on-shell gluon in the intermediate state, it should also be plus or minus 1. And you can't add plus or minus 1 to plus or minus 1 and come up with plus or minus 1. So instead of getting a 1 over Kp squared, there's a angular momentum barrier factor that suppresses this. It also gives you a azimuthal phase angle. And in fact, this sort of behavior is one of the reasons why spinor products, which I'll introduce later, are so convenient, because they sort of exactly capture this kind of behavior. Just for completeness, let's just look at this case. In this case, if we have a helicity plus or minus a half, well, let me put a plus or minus a half here for this quark. For massless quarks, this is a helicity conserving interaction. But usually So going in, this is also has to be plus or minus a half. And it's the same one as this one, whatever that is. Now this can be plus or minus 1, but because the helicity here was equal to the helicity here, we again have a mismatch of plus or minus 1. So in every QCD case, we get this mismatch of plus or minus 1. Just because we're on the subject, let's do gravitons. So gravitons, we'll call them H. The perturbation of the metric is usually labeled by H. They have plus or minus 2. And so they violate helicity conservation by 2 units, not just 1 unit in these vertices, by analogy to here. And so this actually goes like Kp squared to the 0. It gets 1 more power of suppression. This one got 1 power of square root of Kp squared. By analogy, this one gets 2 powers. It still has some azimuthal angle dependence, but it doesn't generate collinear singularities. That's why you never heard of the Altarelli-Parisi equation for gravitons. Also, there's not much data for graviton scattering, but if there were, there wouldn't be any collinear divergences, which have to do with the Altarelli-Parisi equation for gauge theory, which we come back to later. So I hope that sort of answered the question. You can also just go through and plug in these vertices in the collinear limit and see that you get this suppression factor. But I think the angular momentum argument is a little bit more intuitive. Any other questions? So if we come back to this diagram, which for this one loop process, which I sort of turned around, sorry, and I'm going to call this line P1, and this is L plus P1. So this is now a loop momentum L, which I called K before, sorry again. And then this is a Q bar with momentum P2. And this, if these are all outgoing, this has momentum L minus P2. When we use these IConnell factors, which are just proportional to the momentum here, we can pull out a factor, and then this index nu is the same index down here. So we get to contract this index or contract the P1 with the P2. So we get some factor like 4P1 dot P2 coming out front. And remember, it didn't really matter what line this was. Once we took this IConnell factor, this is a bosonic line, which has the form 1 over, this propagator has the form 1 over L minus P1 squared. And I'm not going to really care much what happens in here. I'm just going to write down a formula for the integral over the loop momenta in dimensional regularization, where we always use d equals 4 minus 2 epsilon over the loop momentum. And there's a measure factor of 2 pi to the d. And at this point, I have nothing left in the numerator, and I just have 3 propagators. I have the standard propagator for the gluon and Feynman gauge, which has a, so this is this propagator for the gluon, if I had indices mu and nu, has a delta AB in color, a delta mu nu, and so this is in Feynman gauge. And then on either side of it, well, I also have a propagator L minus P2 squared and a propagator L plus P1 squared. In other words, in the soft limit, all the numerator algebra became trivial because it was just proportional to these external momenta. I get a factor of 2p1 nu from here, and a factor and a delta mu nu in between, and a 2p2 of mu from the other one. But it has no dependence on the loop momenta in the soft limit. Yep. I'm taking the virtual, now I'm taking the virtual gluon that's exchanged between these 2 hard lines to be soft.
So then don't you have to integrate it all the way up to
So I'm cheating a little bit, yeah. I mean, I'm integrating from 0 to infinity. It's technically not, the approximation isn't really correct in that limit. But, so I should not believe anything I see that is finite in this integral. I should only pay attention to the poles in epsilon, which come from this region down below. Now, in fact, they don't come only from the soft limit, because I've also got some collinear divergences in this particular integral too. And so I probably shouldn't even believe the 1 over epsilon terms. Only the 1 over epsilon squared terms should I believe. And they come from the overlap of the soft region and the collinear region. So L goes to 0 is soft. But within L goes to 0, I can also have L dot P2, P1, which is L dot Pi goes to 0 is collinear. So I really have three regions that intersect near L equals 0. I have collinear with line 1, collinear with line 2, and soft. So we could discuss this integral later if you want. I don't want to do it right now. Later on, I'll show you another integral. If you know how to do that one, then you will know how to do this one. But basically, this and maybe I should put in another factor here, since we did cover this. We get the Casimir in the representation R. And, well, I'm assuming that this color line flows back through here, and this generator matrix, TAR, and this one, TAR, get dotted in and summed over. So that's where that Casimir comes from. Okay, let's count powers of the loop momentum. Has a d4 minus 2 epsilon L in this limit. And let's look at what happens when L squared is 0 and also P2 squared is 0 in here. So this has a L squared minus 2P2 dot L plus P2 squared. But P2 squared is exactly 0 if this is a massless line. And this is also 0. So you see we have something scaling at least linearly to 0 here. And this also similarly has a scaling to 0. So we have 4 powers of loop momentum in the denominator. And we have only 4. What? Because I was considering the massless limit. If I had a mass, I would still get the same form, however, because then my propagator would have a minus m squared in it. Okay? And then P2 squared would be equal to minus m squared. So I still have the same form, whether it's massless or not. So the soft limit always diverges, but when you do the regularization, you find that there's a double log divergence in the massless case, because you also have this collinear divergence on top of it. But just working in the massless case again, when you work out this integral, you get some gamma functions which aren't really too important, except I've written them so that they're of order 1 when epsilon goes to 0. But you find a 1 over epsilon squared divergence. And if you're careful about the measure here, you should also have a mu, introduce a scale mu whenever you do dim reg, and you get a mu squared that cancels a fractional dependence on, let me just call this S12, this overall factor here. And this is raised to the minus 1 plus epsilon, but there's also a factor of S12. Actually, sorry. This is raised to the epsilon, and then there's another factor of 1 over S12 that cancels this factor. So the bottom line is that the sort of virtual soft emission factor if I want to be slightly more general, yeah, never mind. It goes like this quadratic Casimir, and then it has, the most important thing is this minus 1 over epsilon squared. And then it has some logarithmic dependence at the next order. When you expand this out in epsilon, this will contain a epsilon times log mu squared over S12. And technically, this should probably be a minus sign. So this is the double pole in the dimensional regularization parameter I was talking about. And that gets canceled on the real emission side, although it doesn't get completely canceled. I mean, this is basically in a different kinematic region. These collinear divergences, the soft divergence is canceled against a soft endpoint of this collinear emission in this process here. But the collinear divergence and a collinear piece of this are not canceled by that graph. And they really correspond to different kinematics, because whereas the virtual correction has the original kinematics in the Born process, here the kinematics have changed because something with only a momentum fraction z is going into the hard collision. And so those divergences can't be canceled by the virtual graph. So they're canceled by the renormalization of the parton distributions. And I'm not going to go into great detail on that, but basically you find that after you have canceled the soft divergences between the real and virtual emissions, you have left over 1 over epsilon collinear poles. And you find that they sort of have a behavior that are proportional to the to various splitting kernels, which show up called PAB. And these are associated with the DGLAP equation. So that equation says that the parton distributions that we were discussing, which depend on x and a scale, factorization scale mu squared, when you change mu squared, even though we can't calculate the, these are non-perturbative quantities, but if we measure them at a large scale, mu squared, and change that scale, we can calculate how they vary. And they have this structure which is denoted, a shorthand for it is this convolution formula. But all it really means is that you need to insert a intermediate fraction z and integrate over it, a convolution integral, so that the product of the thing appearing in the, let me call this y, if I also define x over y equals z. So this will be z, and then I probably screwed something up. Never mind. Okay. So the right-hand side of the DGLAP equation involves a convolution over some functions PAB, which are the splitting probabilities, which we can compute if we know the collinear behavior of amplitudes, multiplied by the parton distributions at another point y, which is always greater in x. In other words, when we have the proton and we extract out of it some parton, but before the parton reaches the short distance process, it and this had momentum fraction y, then if this has momentum fraction x, so x over y is what I was calling z before. The relative fraction that this has relative to that. So this involves this PAB, splitting kernel. So if we move mu squared, we change our interpretation of the structure of the proton logarithmically. And when we end up calculating these collinear contributions, which I'm not doing for you, you have a compensating logarithmic variation in the short distance cross section. So we're moving this gluon in and out of the box for the short distance cross section. So this DGLAP equation is also used to move data taken at different values, effective values of mu squared, to move it from one scale to another for use in all sorts of different processes at the LHC, which is typically a very high scale compared to where the partons were actually measured. And using this whole framework, it's possible to have very accurate distributions. These splitting kernels have been calculated to 2 orders further than this leading order we've been talking about. And so you have very accurate evolution and very accurate data to get at the % to 5% sort of uncertainties for the structure of the proton. This is codified by the parton distribution. Is that sufficient, that accuracy? For the moment, it's mostly sufficient. There are some cases where the data is more accurate than the theory. And one of those is next to leading order. Is Z production. They can measure the Z. They have, as we talked about before, they have millions to billions of Z's. And they can measure in particular, the transverse distribution of those Z's very accurately. And there's about a 4% tension, I think, between the latest NNLO calculations and the experimental data. So that's an example of a place where the theory needs more work because we don't really think that new physics is accounting for that. Okay, before I leave QCD at the LHC, I just want to sketch the kinds of calculations, the kinds of amplitudes that you need to do the NNLO case. So do I dare to try to clean the board here? I know, but I got complaints that I wasn't doing a very good job of erasing last time. You see what I mean? Anyway, I'll at least wet this down and then start over here and let this dry. Because okay, I'll mess up this board. Oh, those are drying. anyway, the NNLO ingredients fall into sort of three generic categories. One is double virtual. So I'll just give you an illustration of it again for the Z process. So those would be two-loop corrections, Feynman diagrams like this. So you can see we now have 4 powers of GS. So that's our 2 powers of alpha S coming from the virtual side. And then we have what are called sort of mixed real virtual. So that's one loop, but one more leg. So an example of that would be where we have the process Z plus gluon, but on one side we use a one-loop amplitude. So here's the Z and gluon in the final state, the same QQ bar initial state, and here I've drawn the conjugate tree amplitude that you interfere it with. So in this case we have GS cubed on this side and GS on this side to get to our GS to the 4th. And then finally we have double real. And there we can have things like 2 emissions of gluons. And then we square this, so we have GS to the 4th from squaring those two. And there's a whole host of other processes in this category and this category that I haven't shown. And there are also many different types of singular regions of the phase space that you have to handle. In the one-loop case, you basically have soft emission, and then neighboring it, you have collinear on either side. But here you can have double collinear, which is kind of off each side, which I've shown here. But you could move this gluon over here, and you could have a triple collinear splitting where a quark radiates 2 gluons down the same direction. And so it's a real hassle to integrate all of these things in phase space. And then on the loop side, for this process, these loop integrals, these loop amplitudes have been known for decades. But when you go from 2 to 1 to 2 to 2, you get to cases that were only done in the last few years. And then when you go to 2 to 3, you go into the unknown. People don't know how to do these 2-loop amplitudes for 3 bodies in the final state, as I mentioned last time. So that's sort of where I wanted to leave the overview of the sort of general QCD structure of processes at the LHC at higher orders in QCD. Any questions about that before we sort of go back to some fundamentals and discuss sort of monitored organization of amplitudes? Yep. For 2 to 300? Okay, so 300 particles come out of a collision at the LHC. The way they do approximate that, most of the time what the experimentalists run is what's called a leading order Monte Carlo. So that has the leading order tree matrix elements in it. For some cases they run it with loop amplitudes included too, but most of the time they run it at tree level. And then what they do is they do a Monte Carlo, parton shower Monte Carlo. Is Leon Tao here? Just wondered if he's going to talk about that. I don't see him though. Oh yeah, are you going to talk about parton shower Monte Carlos? Okay, so this collinear and soft pattern I was telling you about, that is simple enough that people figured out how to iterate it and resum it and do it repeatedly. Okay, so what they do is they take this fact that this P is a probability and they make a Markov chain. They throw dice and they have probabilities where they decide if they have a quark coming out of the process at a given virtuality or a given scale, they decide based on a random number when that thing is going to split into a quark and a gluon, and they randomly distribute that value of Z weighted according to the splitting probability. But then they can go ahead and do it again and again and again. And what they get is generally things that look like jets, except they're still made out of partons. Then at some low scale, they have some rule, which often uses string theory, that is the Lund string model, to calculate how they make hadrons out of these. So these are now going to be things like mostly pions, the occasional kaon, maybe a proton at some point. They have 3 quarks together. So they make hadrons. And then they hand off those events to or the experimentalists run these Monte Carlos, and then they pass those through their detector simulation, the hadrons. So that's how they get to 300 by iterating this branching to high orders as they go from, there's an logarithmic evolution in the virtuality from 100 GeV, or whatever the scale of the hard process is, down to around 1 GeV, which is where the coupling, a few hundred MeV, where the coupling becomes non-perturbative and they switch over to some hadronization model. So you shouldn't necessarily trust things that have to do with the details of hadronization. And the idea is to find observables that don't depend much on what happens at long distance scales. Any other questions? Yep. Not so easily. You really need to, I mean, the soft structure has some aspect to it. Usually there's a high energy behavior. I think maybe we'll talk about that in more detail later, but I mean, offline with you. There is a structure where you can have collisions of gluons. First of all, there's something called the soft pomeron, which has to do with the growth of the total cross-section for pp. That's purely non-perturbative, and you can't see it this way. But there's also something called the hard pomeron, which governs aspects of jet physics. This diagram can be interpreted as a cross-section for some gluons scattering into forward jets that are near where the original gluons were going, plus many more jets laid out along the detector, well separated. And if you draw this diagram and sort of compute it in the right approximation, you will see the BFKL pomeron. And so, yeah, there's a way to see that, but I'm not going to be able to go into those details now. Any other questions? Okay, now that I have a few clean blackboards and a clean slate in 6 minutes, I can say a little bit about sort of modern amplitudes. And now I'm paying the price for not drawing the screen here. Was there a drying rag somewhere? This thing, a squeegee, yeah. So there's 2 aspects to this organization. One is what's the right way to, or what are different ways to handle the color organization, and then also kinematics, and we'll only get to start color here. So for simplicity, we're going to consider adjoint theories. You can do similar things when you have quarks like in the fundamental, but just for reasons of time, then all vertices, the only color structure that you get is the structure constants, which are also the generator matrices for the gauge group in the adjoint representation. And the thing about the FABCs, and we're going to denote this diagrammatically. So in this section about color, when I draw a diagram, I'm just going to steal the Feynman diagram notation for the color factor. So this is FABC diagrammatically. So then I can write the fact that TA, TV is FABC, TC. I can write down that in the following way. Well, I changed the indices a little bit. Maybe I should call it TB, TC is FBC, TE. Sorry. Anyway, so if you plug in these structure constants, the F's, you get nothing more than the Jacobi relation. You all remember the Jacobi relation, right? Which has two F's, three terms, each of which have two F's contracted together in different ways. And this gives you the rules for contracting them. Now, that leads to an ambiguity in how you represent the color amplitude, the color structure of the amplitudes, because you have some freedom with this. And there's sort of two approaches to dealing with it. So one approach is to introduce a new, something that you technically don't need, but it's very useful, which is the generator in the fundamental representation. And this leads to something called the trace basis. And this is particularly useful when you're thinking about the planar or large NC limit. But it can be used outside of the large NC limit, certainly. And then another thing you can do is you can solve the Jacobis in a sort of in a natural way. And this direction will lead us into something called it's particularly useful when you're very interested in what's happening at finite NC, which would include at the loop level non-planar and to relations like there are some relations called the Kleist-Coif relations and the BCJ relations. And they all are done in a little different way. So since I'm running out of time, next time I will go through these two and we'll derive the Kleist-Coif relations, and then we'll move on to the sort of kinematic basics after we get the color structure out of the way. So, any last questions? Yep.
I have a question for last
Sure.
time. So you mentioned that difficulty in combining three little diagrams with continuation.
If you want to, integrate over the loop momenta, you should have the right causal structure. Yeah.
Yeah. So I mean, what goes wrong if you just do the most 90 things? Or several times at a time? Like, what should that look?
Yeah, it's how you continue back. You have to know where the singularities are when you do the continuation. Or you mean if you know work it out analytically, work out the integration analytically, then you know how to continue it analytically. Yeah. Yeah, in principle, that should work. There's also the little bit of a sociological issue that while we have Amplitude's conference every year, I've joked that we should spin off an Integrans conference because there's a group of people that are more interested in the structure of the integrans than in integrating them. And the ones who are producing new formulas for the representations of the integrans haven't always been the ones who would like to integrate them. So, but yeah, in principle, what you say is true. If you are, powerful enough, if by going to the Euclidean region you can make manifest, well, I should also say the following. You can't always go to a Euclidean region. That's one of the problems. If you have suppose we have this box integral, and suppose we only know it when all the lines are massless. Then it's a 4-point process. We can use the Mandelstam variables S, T, and U to describe it. And this thing will have branch cuts in the, let's call this S and this T. So this will have branch cuts if S is greater than 0 and branch cuts if T is greater than 0. So if we want to have a Euclidean region for it, we do have one choice, which is to the U channel corresponds to these two particles coming in. And so if we work in the channel where U is greater than 0 and S and T is less than 0, then that's a Euclidean region. And we could do the same thing at 2 loops for this box integral. It only has cuts this way, it has some cuts this way, but it has no cuts in this U channel. But then you go non-planar at 2 loops. And this has cuts in all 3 channels. So even when you have a local form for it, it's actually somewhat complicated to figure out the full analytic structure because there is no Euclidean region for it. It has branch cuts in all channels once you've decided that all the particles are massless. Sometimes people cheat, take some of the, or they violate the Mandelstam relations temporarily in order to identify Euclidean region for some generalized process that they can come back from. But it's not so simple all the time. Any other questions?
Maybe we can continue during the break.
Okay.
Yes, thanks.
Keep us moving.